Welcome student, I am Shadev Hake, ANTC Department, TICT Pune. Today we are going to perform a new experiment of RMT subject, that is directional coupler. So our title is to measure and verify port characteristics of directional coupler. So our objectives are study of directional coupler, and second objective is nothing but to determine the parameters of directional coupler like a coupling factor, insertion loss, isolation and directivity. Yes. So let us see the simple block diagram related to the directional coupler. Then we will see the small theory related to the directional coupler, and then we will perform actual practical of directional coupler by using the X-band setup. So this is a simple block diagram of directional coupler. Already we have seen this block diagram in a E-plane T, H-plane T and magic T. So in our directional coupler experiment, our first block is a power supply, klystron tube power supply. We know the operation of klystron tube power supply. Second block is a klystron tube, or it is also known as a reflex klystron tube. We know in our experiment we are using a klystron tube as a oscillator. This oscillator generates a microwave signal in a X-band. Our third block is nothing but a isolator. We know the operation of isolator in our block diagram. This isolator avoids the reflected signal from the output side, and it keeps the stability of your oscillator, means operating frequency in a stable position. Next block of our block diagram is nothing but a cavity resonator. Already I told you many times that here cavity resonator work as a frequency meter, or it is also known as frequency meter, because our oscillator generates a microwave frequency, and this microwave frequency we can't measure by using the DSO, CRO or multimeter directly. So for that purpose we require a cavity resonator, means frequency meter. Our today's experiment is a directional coupler. So our this block is nothing but a device under test. Our DUT, device under test, of today's practical is nothing but a directional coupler. Yeah. Here we will see the working and construction of directional coupler, but in our block diagram, our next block is nothing but a detector. Here detector is used to detect the electromagnetic signal, and those magnitude of detector will check on a CRO or DSO. Okay, so this is a simple block diagram of directional coupler. So first of all, see the actual construction and working of directional coupler, and then we will see how to measure the parameters of directional coupler like a coupling factor, insertion loss, isolation and directivity. Yes. So if we see the actual structure of directional coupler, it looks like this. This is my directional coupler structure. Okay. So in which, look here, this directional coupler is made from the two waveguide. One is a primary waveguide and another is a secondary waveguide. So structure and working of directional coupler I will explain on a board first, because you can understand very easily how we can design a directional coupler by using a two waveguide. Yes. So if we check the front view of this directional coupler, it looks like this. This is a front view of directional coupler, in which my this waveguide is a primary waveguide. Primary waveguide, or it is also known as a main waveguide. Primary waveguide has a two port. This is our first port and this is our second port. We are looking a new device, that is a directional coupler. Directional coupler means indicate that your primary waveguide couple some amount of power into the another waveguide. That's why we are using another waveguide, that is a secondary waveguide in a directional coupler. This waveguide is known as a auxiliary waveguide, in which this port will refer as a port number 3 and this port will refer as a port number 4 in a directional coupler. Let us see the working of directional coupler and then we will see its parameter. Suppose consider here apply the input to the port number 1, means I will apply input to the port number 1. What we will do, we will match a port number 2. We will match a port number 2. We will match a port number 3. So what happened actually? The meaning of directional coupler. This direct main waveguide couple some amount of power in a secondary waveguide. And this coupling can be possible by using some holes in between the primary and secondary waveguide. If we see the open surface of your waveguide, upper surface, yes, you look, you will get a numbers of holes. Yeah, and these holes will indicate your directional coupler magnitude, means 10 dB directional coupler, 20 dB directional coupler, or 40 dB directional coupler. So types of directional coupler, means dB of directional coupler is totally depend upon the numbers of holes in between the primary and secondary waveguide. Yeah, or main waveguide and auxiliary waveguide. Got my point? So what we will do here? Here we will match our port number 2 and port number 3 and we will check the output across a port number 4, and this output is nothing but a coupled output. Coupled output. That's why our first parameter related to your directional coupler is nothing but coupling factor. Yes. So according to the definition, or according to the structure and working of directional coupler, the definition of coupler factor is nothing but it is the ratio of input power to the coupled power. So here, in which we will refer the input power as a P in here, and we will use a coupled power, that is a PF, across a port number 4. But in our actual practical, we are not going to measure the power. We are measuring a voltage with respect to the electric field. That's why we will use my input voltage, that is a Vin, and coupled voltage, that is a Vf. And according to the definition, the coupling factor is nothing but ratio of input power to the coupled power, and hence my formula would be, according to the voltage, 20 log of input voltage to the coupled voltage. Yes, this is a first case related to the directional coupler. By using the we can check the directional coupler performance by using its parameter, and this is your first parameter, that is a coupling factor. My second parameter is nothing but a insertion loss. So insertion loss. Yeah. So to measure the insertion loss, what we will do? We will apply the input to the port number 1. We will match your port number 4 and port number 3. Yeah. Whatever be the output across the port number 2 is nothing but your received power. But already I told you we are not measuring a power, that's why we will replace this power as a received voltage. So in our actual block diagram, what we will do, we will use here the second port as a output and here fourth port as a match. Here also third port as a match. I will write here. Yeah. So according to the insertion loss definition, it is a ratio of input power to the received power across a port. Yes. So my definition is 20 log of V in divided by VR. Yes. My third parameter related to the directional coupler is nothing but a directivity. Yes. So in our directivity, what we will do? We will apply the input to the port 1. We will measure the output across a port number 4 and port number 3. So here we know the voltage or power across the port number 4 is a coupled power. But look here, operation of your directional coupler. Your directional coupler will not only couple the same amount of power towards a fourth port. Fourth port is your forward port. It will couple the some amount of power towards a back port also. Such a power is known as a PB, back power. But I told you, if we are not measuring a power here, so we will refer a PB. Yes. Yeah. So we will not refer a PB. We will refer a VB. Voltage across a port number 3. Yes. So according to the directional coupler theory, the insertion loss is defined as, according to the directional coupler theory, our third parameter is nothing but a directivity. And this directivity is nothing but, it is the ratio of coupled power to the back power. And hence I will write 20 log of, in bracket, VL divided by VB. This is a directivity. And my last parameter related to this directional coupler is nothing but isolation. Yeah. For a good directional coupler, your power should not be comes across this port. Ideally, the power across a port number 3 should be equals to 0. If my power across the port number 3 equals to 0, then according to the definition, according to the structure, I can say the definition of isolation is nothing but it is a ratio of input power to the back power. It is the ratio of input power to the back power, and hence we will replace a power in terms of a voltage. So we will write 20 log of V in divided by VB. V in divided by VB. So ideally, if my back power is equal to 0, means denominator is equal to 0. So log of this value, it should be equal to very low, means a 0 dB. Very low. It should not be happen. Isolation should be perfectly isolated. Means port 1 and port 3 should be isolated. That's the meaning is your directional coupler is a good directional coupler. And according to this power, we can identify which type of directional coupler we have. 10 dB directional coupler, 20 dB directional coupler, or 40 dB directional coupler, or else. Yeah. So this is a simple theory related to the directional coupler. Now we will check all the parameters in our actual experiment, and we will check in our lab which type of a directional coupler we have, like a 10 dB directional coupler or 20 dB directional coupler. We have a 2 directional coupler in our lab, 10 dB and 20 dB, and by using the calculation we will verify is it correct or not. We saw actual theory and some parameters related to the directional coupler, but look here, this is your actual directional coupler. Yeah, practical directional coupler, in which this directional coupler is only 3 port. Yeah, 4th port is available, but it is match port for your simplicity. Okay, so how we will measure here? Look here. If I place my directional coupler here like this, so this is my input port, means this port. Here, this is my output port of primary waveguide, means this port, and this is my coupling port, that is the output of secondary waveguide or auxiliary waveguide, that is this port. So in this case, this is my V in, this is my VR, and this is my VF, forward coupled power. Yeah, this is the case number 1 to measure the V in, VR and VF. Got my point? Yes. Now, in second case, means we have to measure this parameter, that is a back power or back voltage. At this time, what we will do? We will change the position of directional coupler like this. Look here. This is the position of directional. So in which we will apply the input to this port, means primary waveguide. Here we will get the output, that is a VR voltage. It is same, no change in a first and second case. But whatever with the voltage across this port, or whatever with the power across this port, is nothing but a back power, that means this power. So look here, this port is my input port, this port is my received port, means this port, and this port is nothing but my back power port, this port. So in this way, we will measure the 4 parameters related to the directional coupler, like input power, received power, back power, and forward coupled power. Okay, so actual performance of this directional coupler we will see on a X band setup, which is already available in our lab. Thank you.
Hello students, welcome to Radiation and Microwave Technique Laboratory. Today's experiment is related to port characteristics of directional coupler. In a theory, it has been already explained how this port analysis can be carried out related to directional coupler. In reality, how it looks in a waveguide structure is this device. This is a passive device. It consists of total 4 ports. If you look into it, the bottom line is one waveguide, to which we can call as main waveguide. On the top of that, you can see the another waveguide that we called as auxiliary waveguide. It is coupled internally at the one side of the waveguide, and that's why there it can have two different types of holes technique, two-hole technique and multi-hole technique directional coupler. This directional coupler is multi-hole directional coupler because internally where it has joined, it has multiple holes into it, not only two. So it is multi-hole directional coupler. Let us understand the port number that we can assign to it to understand its port characteristics. This port I can say as an input port. Exactly opposite to that, I can call that as received power port. So input signal I can apply, I can get the direct signal to the port number 2 as a received power. Whereas you can look here, the fourth port is closed, which is matched with proper impedance matching. This is permanently fixed port. Whereas port number 4 is open. That port, power whichever we will receive, that power is called as either forward power or it can be coupled power. As it has been already explained in the theory, the use of this directional coupler. It can be basically used for two different purposes. The first purpose of it is whenever we need to give partial amount of power to some another extension device, we can use directional coupler. So main power I may apply to the main line, and the amount of coupling which we require to give it to the extension circuit, for that number of holes can be managed and power can be extended to the another circuit. So likewise, coupling factor we can decide with the help of directional coupler. Another use of directional coupler is to measure the impedance through reflection coefficient. That we will see in some of the experiment. Now let us understand what are the parameters that we can verify in this experiment. So first parameter is coupling factor of the directional coupler, insertion loss of the directional coupler, then directivity of the directional coupler and isolation of the directional coupler. These are the 4 important parameters that one should understand while studying directional coupler. To go to real experimental part, let us understand the microwave bench setup through which we are going to measure or verify the port characteristics. Setup is already done over here using X band. So X band is 8.4 gigahertz to 12.2 gigahertz. This is the power supply which we use to drive the reflex klystron tube, which is generating X band frequency. The total setup is designed for X-band setup. So as the frequency is huge, the waveguide size becomes small. If it is in the C band, it would be a large size of waveguide, and then it will be difficult to have the setup and the total measurement. It becomes tedious job. So for laboratory observation and verification of the microwave devices, particularly X-band is preferred. So the power supply setting we will understand now, which we need to bias reflex klystron. If I switch first to display the beam voltage, reflex klystron, it has few biasing potentials. Out of that, beam voltage is 1, beam current and repeller voltage. So as per the requirement and the setting, repeller voltage is set in such a way that we will get beam current. Okay, so let us understand the power supply setting which we need to bias the reflex klystron. In a setting, reflex klystron has a beam voltage. So that beam voltage we can set in such a way that at the output of this setup will get square wave output and with some magnitude. So beam voltage, here it is set as 248 volt DC, and that voltage has been also set in such a way that beam current should not go beyond 20 milliampere. So it is now 13 milliampere. Repeller voltage we can set to get the different mode, like mode 1, where we set whether mode 1, mode 2 or mode 3. In general, we set reflex klystron mode 1 so that we will get better magnitude and perfect square wave. Let us understand the setup components so you can understand the setup and the sequence of the setup. This biasing potential is given to the reflex klystron. Cooling fan is essential because as it is continuously operating, it is generating some certain amount of heat. To cool the reflex klystron, we need to have a cooling fan. Reflex klystron, as we have seen, it is used as a source of X-band frequency. That source should not damage because of the mismatch into the impedance. In transmission line or in case of such kind of communication, impedance is one of the important parameter, where if it is mismatched, there will be reflection. To avoid the reflection and the return path of the power towards the source, we can avoid by using isolator. So reflex klystron, then there should be an isolator which will isolate between input and output devices and the component. Then attenuator, if we want to reduce the power of the reflex klystron, which is 0 dBm or you can say 1 milliwatt maximum, that you can attenuate by turning this microwave gauge. After the isolator, there may be a variable attenuator. This is optional device. If you want to reduce power, you can reduce the power by changing the level of the screw so that it will reduce the power. Then another component you can observe here is frequency meter, which is working on the cavity resonator principle. So if you turn it, you can see different observation on the screen that we will see later on. As it is not tuned now, while measuring the frequency, we can understand the frequency meter can be used to measure the frequency inside the waveguide. If at all student want to measure the frequency which we are saying in the X band, that can be measured using this frequency meter. It works on cavity resonator principle. So if you turn it, whenever it resonates, it drops down the volt magnitude so that it is working at as a notch filter. So I am just turning it. You can observe whenever it is matching, it is resonating, it will be reduced magnitude of it. Here. So here we can say it is almost resonated, where that square wave magnitude is almost dropped to negligible potential. If I detune it, if I start changing the position of the resonance, if I detune it, it will give again back the maximum magnitude. This is called as resonance and the tuning of cavity resonator to measure the frequency. So where it is tuned, that frequency you can measure with the help of the parallel to red lines coinciding to the vertical line. That will be the frequency of the waveguide in X band. Now let us understand how we can give the input to the directional coupler. We need to give input to port 1. We can measure output over here by matching the terminal 3. We cannot keep any terminal open. As such, fourth port is already closed. We should close this with the match terminal so that I can be able to measure the received power by giving input to it. Another parameter is to measure the forward power. If I give input to the port 1, I can be able to measure over here using diode detector by matching load termination to the port number 2. So it will match, the power will be coupled through the holes, multiple holes, and it will come out through port 3. That will be either forward power or coupled power. So we got now two parameters of the two voltages of the directional coupler. Now let us understand how input voltage we can give and observe all the four parameters so that all the port characteristics can be verified. To measure the output of this reflex klystron setup or microwave bench setup, first of all understand what kind of signal that we will get at the output of this microwave bench setup. Whichever output voltage and the signal that we will get at this port, that can work as an input which we can give it to the port number 1. Now before applying it to the directional coupler, let us understand what kind of signal that I am getting at the output of the setup of the X band frequency. This component we called as diode detector in X band bench. Internally it has a diode, Barrett diode, which works at X band frequency. If I connect this diode detector to the output of bench, we can observe here a square wave signal. Now there can be a confusion what kind of signal the reflex klystron is generating and how it is possible to observe it on the oscilloscope. Because oscilloscope bandwidth, if you observe here, it is mentioned 40 megahertz only. Whereas this reflex setup, klystron setup, is going to operate at X band, which is nothing but 8 to 12 gigahertz of frequency. So for experimental purpose or for a laboratory purpose, this setup is made in such a way that students should able to understand the signal or to understand the power or the voltages so that we can understand different parameters of different passive components. X band frequency is generated by reflex klystron. If you understand this power supply, through this power supply we are applying a modulating signal to the reflex klystron, which is in the frequency range of 1 kilohertz at the max. This modulating signal is modulated in amplitude modulation form, and that amplitude modulated signal, that means the modulating signal of 1 kilohertz will modulate with the X band frequency in AM form, amplitude modulated form, and then that will launch into the waveguide and it will come out of the end output. So using this diode detector, which has a diode into it, if I couple over here at the output and with proper matching, impedance matching, power will not reflect an exact amount of voltage that I can able to see. So output which you are actually observing is the demodulated output. As I told you, the square wave 1 kilohertz approximate frequency signal is applied to the reflex klystron for the modulation. So at the output you can observe here as a square wave. So let us understand the square wave and what is its voltage. So this total signal and its magnitude is nothing but the input to the directional coupler. So let us start with the experimental part. So after connecting the diode detector, the input voltage we need to calculate different parameter is 2.84 volt. This is V in. So I can write here V in as 2.84 volts. Similarly, I should write how much is the beam voltage. So beam voltage is 247 DC. Beam current is 14 milliampere. And as I said, frequency we can measure with the help of frequency meter. If I turn this resonator wherever it match see, it is reducing and it is a notch kind of filter. So it has dropped to the voltage around 1.8 volt. So I can measure frequency. This is between two red line and where vertical is coinciding. So it is in between 11.05 to 11.1. So it is almost 11.075 gigahertz of frequency. So if I detune it, I'll get again square wave output. So it is 11.75 gigahertz. Now let us measure. Now connect the directional coupler and measure the received power at the main line. Now directional coupler is connected to microwave bench. So the output of microwave bench is become input to the directional coupler at port number 1. To the port number 2, I have connected a diode detector, and port number 3 I should not keep open, so I am terminating it with the help of match termination. So it should match with perfect rectangular gap. So it should not be crossed, so that E field and H field will not cross. So it should match direction perfectly. So I am matching port 3 with the match load. So I am just repeating, I have applied input to port 1. I am observing output using diode detector at port 2. So V in and the measured voltage is V received, and this voltage is 2.76 volt. So I can say, write VR received power is 2.7 volt. Now measure the third parameter. So I will disconnect. Now let us move to second observation. Now again input is applied to input terminal port 1. Port 2 is perfectly matched with the match termination, and I am observing the signal magnitude at auxiliary port number 3. So diode detector is connected to the port 3, which will give me VF or coupled power. So you can see here the output which is connected to CRO is 920 millivolt. So I can note down this auxiliary line VF or coupled voltage is 920 millivolt. To measure the third parameter, that is the back power, we cannot directly connect signal here and measure this output at the closed port because it is the closed port. So what we can do is we can apply signal to the port 2. So I can reverse the direction, and then this port I can couple to the microwave bench, and then I can observe output at the coupled port. For the back voltage measurement, we have reversed the position of port 1 and 2. Port 2 is coupled to microwave bench, and the output of microwave bench is coupled to the port 2. Whereas port 1 I cannot keep open, so I have terminated it with match load, 50 ohm match load. Port 3, where I can measure the back power. So when I am giving input to port 2, and if this is closed, so the power will turn back and it can able to come out through the port 3. So you can observe at port 3 minimum amount of signal is back. You can observe it is somewhere. This is what is the square wave, and the magnitude is around 6.64 millivolt. So we can note down VB at the auxiliary line is 6.64 millivolt. This we have done for 10 dB directional coupler. Now let us calculate
battery 10%.
Now dear student, as we are performing this experiment for 10 dB directional coupler performance and its characteristics, so this 10 dB parameter, it is the parameter related to coupling factor. So let us see by after the observation what is the coupling factor, insertion loss, directivity and isolation. So by calculation I can say it is 20 log into the bracket V in is 2.84 divided by VF, which is coupling voltage or forward voltage, nothing but 0.920. So I can get the coupling factor in dB as 9.79 dB, which is almost similar to the characteristics which is given in the specification of directional coupler as coupling factor 10. Let us move to the insertion loss. Insertion loss we can calculate. For that we need again 20 log into the bracket V in is 2.84 divided by received power 2.7 volt. So I'll get that in dB as insertion loss 0.43 dB. It should come as low as possible. Now let us move to the third parameter, that is nothing but directivity. So to calculate directivity, again we can use 20 log into the bracket V forward. V forward is 0.920 volt, 0.920 volt divided by back voltage, which was 6.64 millivolt. So it is 6.64 millivolt. So it comes 42.83 dB. Now let us calculate isolation of the directional coupler. It is again 20 log into the bracket V in is 2.84 volt divided by VB is 6.64 millivolt. So it is having isolation in dB as 52.62 dB. So these are the performance parameter of directional coupler at 10 dB coupling factor. Similarly, you can continue with 20 dB directional coupler. Same procedure you can follow, and you can observe the performance parameter of directional coupler for 20 dB, 30 dB, 40 dB as per the application requirement. So with this complete setup, you can understand the performance parameter of the directional coupler. Thank you.